Welcome back. Thanks for joining me for another video. Today we're gonna make some cool patterns with geometry nodes using the Fibonacci sequence and the golden ratio. And in case you're not familiar with what that is, it's a mathematical concept that also appears in nature quite often. And what we're gonna build today is a pattern that, for example, appears in the seeds of flowers. So, without further ado, let's jump into Blender, and I'm gonna invert my selection to delete everything but the default cube. And then I'm gonna delete the default cube in edit mode so that we keep the object, but we don't have any data. And then I'm just gonna name it to Fibonacci. And then let's jump into geometry nodes. The reason I keep this mesh is that now we can apply a geometry nodes modifier to it. Ideally, we could do this with an empty, but that's not possible. So here we go. We have this mesh that's empty. Let's add geometry nodes to it, create a new geometry node setup, and call it Fibonacci as well. And I want to add points. So let's start with some points, plug that into the output, and now we have a little point sitting there. And we can also see it over here. We have a point index is 0, position is 0, and that's what we have. We can create more, and then this list goes, increases. It would be nice to have this count available in the settings, so let's do that. And now we can control it over here. But we only see one point because they're all sitting in the same location. One way to immediately see all your points is you can combine X, Y, and Z into a vector. So combine X, Y, Z. And then, for example, we can look at the X position. We can move that based on the index of our points. And the index is this first number in this first column. And that starts with 0. So X starts at 0, this is our first point, and then the second one is index 1, and then the X value would be 1, 2, 3, and there we go. Now we can control it like this, and that is already very cool. We could already sell this on the Blender market. All right, let's continue. I would also like to control the radius in here, so now we can do that. And let's see. The first thing I want to change here is, before we're going to do anything circular, is I want to be able to animate this in a nice way. So currently what's happening, if we animate the count, for example, so I want to make this grow, I want to increase the number of points over time. So if we do that right now, the points just appear, and the first point appears at the origin, the second point appears at X is equal to 1, and they just appear out of nowhere. What I want to do instead is I want to start my first point in the center at the origin, but then I want to let it move out, and once it's far enough, I want to let the second point appear in the center. So instead of setting the location by the index, I kind of want to set the location using the count. But first I want to turn this count into a float, because currently it is something called an integer, which is just a whole number. And that doesn't allow us to animate it smoothly. So instead of an integer, I want to turn this into a float and leave the rest as is. And it's kind of weird to call this count now, because it can be like a 1.5 or something, but I think we can just let it, leave it at count. Now I can smoothly animate this, And if we set the count to our X location instead, we can smoothly move the points. But now again, all the points are sitting at the same position, as you can see here in this list. So to offset the next point to be behind a little bit, I can subtract the index. So having the index available allows us to differentiate between the different points. So that's useful. So let's subtract from this count. I want to subtract the index. So the later points will be behind instead of the opposite. So now we get something like this. We still get this row of points, but they're moving out and they're appearing not quite in the center, but they're appearing at X equals 1. Why is that? That's because we're converting this float into an integer. And if you have something like 3.6, the integer will be 3 if you just convert it like this. But we have a node to convert to an integer called float to integer. And we can use this and round it, or we can use different methods to convert. So if you round it, once we're at 0.5, we start to round up to 1. And that is why it appears at the 0.5 mark. So now all the points start to appear at 0.5. We can also use something called ceiling, which is if we are at 0 point something, it will always round up to 1. So now the points tend to appear more in the origin. And that's already a lot better, but I want to make it even smoother by letting the points already sit here and kind of wait before they start moving. And the way to do that is simply by adding more to this count. And that's a way to kind of have some finer control over when the points start to appear. So now they start to appear before the origin. And we have like a negative distance here. So the last point has this negative X value. But if we want to make the points wait at the center before they start moving, we can move any negative values. We can turn them into 0 simply by taking this position that we're calculating, taking this and setting a maximum of 0 here. So we have two inputs and we're going to take the maximum. And if you set the maximum of the second input, or if you set the second value to 0, any negative value now becomes clamped to 0. So if we disable this node, you can see it's negative and now it becomes 0. So now this point is sitting at the origin, kind of waiting, and then it goes off. And that's kind of cool. All right. I think I want to make them appear at -1 so that there always is a point, 1. So there's always a point waiting there. And that's a little bit better, but now it looks like this point, there's this one point just stuck there. And it's not quite true, but it's always the moment the point starts moving, the next one is already sitting at the origin. So it's, and also one other thing, we are sitting at 0 and then we very abruptly start moving. That's because we take this maximum and we're clamping it to 0. What we can do instead is using a smooth maximum, which is really nice. And then we have an extra value called distance, and this is how smooth it is. So now you can see it starts kind of smoothly moving already. And then the next one appears. And that's pretty cool. So that's a lot better. We can make it slightly less smooth by decreasing this, or more smooth. And now it's like affecting multiple points and they're kind of taking off slowly now. But I want to set this to something like 0.2, 0.3-ish. All right. One last thing I want to do to make these points appear more smoothly, let's make them a little bit bigger, is I want to make them grow and scale up out of nothing. So scale from 0 to the final radius. And in order to do that, we can disable this and see. Now we can see some negative values here. And whenever this value here is negative, I want to make the radius smaller. And this is a little bit complicated math, but we can make this very simple by using a map range node. And also what I'm going to do to organize this a little bit better is I'm just going to copy these 3 nodes and duplicate them over here. And here we're going to have this separate section where we're going to calculate the radius. So instead of this radius, I'm gonna, let's first use this map range node. So I want to map based on this value, and this value, I want to have it be the maximum. I want to move it from 0 to the radius that we control over here. So that's the final output. But then the input is going to be something negative, and we start at -1 all the way here. -1 is the lowest we will ever get in this case. So I'm going to start this at -1, and then when it hits 0, I want it to be the maximum radius. And now we're calculating this kind of dynamic radius. So let's plug that in and see what it looks like. So now that point disappears because the radius is pretty much 0. And then it slowly grows. And when it hits the origin, it's the full radius. So now it kind of moves like this. And then when we enable this smooth maximum again, they're kind of waiting at the origin and growing before they start moving, which is pretty cool. And what we can also do to make this a little bit more smooth for animation is take a smooth step instead of a linear. So what this linear does is pretty much, let's see, this linear is like clamped at between 0 and 1 or whatever you set here. But let's say 0 and 1. So this is like this linear line, but these corners are kind of sharp. So if you choose smooth or even smoother, it becomes something like this instead, which is a little bit smoother. So I want to do that. So let's look at the smoothest one, smoother step. And that looks like this. So now they're kind of growing and moving out. This is our first setup. Let's organize a little bit. I'm just going to remove this and get this back to smoother step. So here, So here with these three nodes, we're pretty much calculating the radius, right? So let's join them and let's call this calculate radius to keep things a little bit more organized. And we could duplicate this and plug the count in here to keep things a bit more separated. So with these ones, we are calculating the point count. And that is pretty simple, but... And then here we are pretty much calculating the distance from the origin. So yeah, let's call that distance. So here we are calculate distance. And now we have a little bit more of an organized setup. Okay, cool. So before I go into the circular pattern, there's one thing I would like to be able to control, which is the distance or the spacing between the points. So currently that's always exactly 1 because of this index. The index goes from in steps of 1. So the distance here is 1. I would like to be able to control that. So after we subtract here, I would like to multiply this with some other setting that we come up with. And now we can control that over here. But I would like to expose that into the settings and call it, instead of value, call it maybe the spacing. And now we have a count, radius, which is a distance, spacing, which is also a distance. And yeah, that looks good. So now we can control the spacing, we can control the radius and the count, and we can animate this. Okay, now let's talk about this circular pattern. Let's see. So to keep this super simple, the simplest way we could create a circular pattern, let's look at it from the top, is if we have one point, we just move it in the X direction, right? And then we have some kind of angle. So let's draw this. So we have the first point, index 0, just moving like this. Then the next point, we want to just rotate an arbitrary angle alpha, and then we move it in this direction. That's going to be index 1. And then we're going to take that same alpha angle and move it again. And then we keep rotating like that. So we need, here we're calculating a distance, but we should also calculate an angle, and every point will have a separate angle as well. And currently we're just plugging the distance into the X, which makes them all move in a single line. I'm just gonna plug something else in the Y direction. Let's start with another index, and that will move the points up, or that will make them start higher up in the Y direction. And I want to be able to multiply this. And in order to calculate an angle, let's say, oh, we're kind of capturing these nodes now. Let's Alt P on these and move them over. So here we're calculating a distance. Here we're kind of calculating an angle. So let's join them together in another frame. All right. And now I'm able to control this a little bit more. And here we're putting the distance in X and the angle in Y, which doesn't make any sense. So we're gonna fix that in a bit. But here I would like to be able to provide an angle in degrees. So we have to convert degrees to radians, not radius. Radians, yes. So now you could say 45 degrees, for example. And then that will be converted into radians, which is the way, if we use like math nodes, they all rely or they expect radians. So we have to convert to radians for that to work. But what we're doing now is we're having a distance and an angle, and we're putting them into X and Y, which doesn't make any sense. Distance and angle is kind of like a polar coordinate system. X and Y is a Cartesian coordinate system. So if we have some kind of angle alpha and we have a radius or distance r, then what is the X value and what is the Y value? Well, the X value is the cosine of our angle and times the radius. And that's our X. And our Y is equal to the sine of the angle times the radius. And you can read more about this if you want on Wikipedia. And we're pretty much converting from a, let's see, we're converting from a polar coordinate system, which is based on an angle and a radius. And we're converting it to a Cartesian coordinate system. And yeah, you can read more about that if you are interested, but I'm just gonna show this to recreate this in Nodes, which is pretty simple. So I kind of want to start with the angle. So let's move this around. And I want to start with calculating the X, which is gonna be the cosine of the angle times multiplied by the distance or radius. And that's going to be our X. And our Y is very similar. So let's duplicate these nodes to calculate the Y. We're going to plug in the angle again into this one, and it has to be the sine. And then we're going to multiply that with the distance and plug that into the Y. And we're not looking at our... So now the angle, we're having a 45-degree angle. So what should happen is the first point should move in the X direction. But then the second one should move 45 degrees rotated from that direction. So let's see if that works. Yep, that seems to work. And then the third point should move straight up because that's 45 plus 45 is 90 degrees and so on. And now we're creating this kind of spiral pattern, which is kind of cool. And I'm not able to move this very far just by the scale of this count. So what we could do now is maybe animate this. So at frame 1, I want to set this to something like 0, which rounds up to 1 point. Maybe we go minus 0.7 or something. Because what we're doing here is we're taking this count and we're adding 1 to it. So that's why we already see something at 0. So let's add a keyframe and then maybe go to frame. Let's set the end frame to 1000 or something and go to the end frame and put this at 1000 points. And that's kind of crazy, but let's see. And we can reduce the spacing to see what's going on a little bit. But when we move out, when we zoom out, we can see this very clear pattern of pretty much lines rotated by 45 degrees. So the angle is something we want to play with, and that's where Fibonacci comes in. So if we move to some random angle, you can get some really interesting patterns. And let's look at how this looks when we animate it. So we kind of, it's already very cool. But the way a flower would put the seeds in is, if it would put the seeds like this, it wouldn't be a very effective flower because there's a lot of space kind of wasted. So a flower would like to put the seeds, it's beneficial to put the seeds in a more evenly distributed pattern. And that's where Fibonacci comes in. So we can find angles that kind of look really well distributed and really kind of random. Something like this looks pretty good. And if we animate this, we can get some very interesting patterns. But to find the best possible angle here, we're going to use Fibonacci. So let's quickly talk a little bit more about Fibonacci. And I'm going to make this bigger. Oops, that's the wrong screen. All right. So the Fibonacci sequence is a sequence of numbers, and it starts with 1, 1. You can start either with 0, 1, 1, 1, or 1, 2. But from there, the next number is the sum of the previous 2 numbers. So the next number is the sum of the previous 2. So we have 2, so the next number is the sum of these 2, which is 2. Then the next number is the sum of 1 and 2, which is 3. The next one, 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 21. 34. 55. And so on. And we can look at Wikipedia to find more about this. This is the start of the sequence. And then we see these cubes. So this sequence, let's go back to Blender. What the heck has this sequence to do with angles? Well, so far not much. Another interesting pattern where you can see the sequence is if you start with a square of size 1, so the length of the sides is 1, and you put a next square next to it in one of these 4 directions. Let's start with the right direction. So let's put another square that the size is 1 as well. Then we rotate 90 degrees and we go down and we put a square into whatever we have here. So that's going to be a square of size 2 because the length of these 2 is 2 together. And then we rotate again 90 degrees. So we have to go to the left and we put a square across this length, which is now a length of 2 plus 1 is 3. And then we go 90 degrees again, and so on. We keep going like this. And this square will be 1 plus 1 plus 3 is 5. This square will be 2 plus 1 plus 5 is 8. That's not a square, but you get the point. And then this will turn into some kind of spiraling thing that also has this sequence, which is kind of cool. But we have to talk about something called the golden ratio, which kind of emerges from this sequence. So if you take any last two numbers that you come up with, you can create a ratio out of those. So a ratio is pretty much always two numbers. So you might know the aspect ratio of your renders. So if you render at 9020 by 1080, your aspect ratio is 16 by 9. And if you divide 1920 by 1080, you will get the same result, which is like 1.7 or something. The golden ratio is actually almost the same as this aspect ratio, which is something like 1.6. Would also be called phi, which is this symbol. But you get this golden ratio if you divide 55 by 34. You get something close to the golden ratio, and as you move into the sequence, the next number will be 89 and then 144. So the further you go in this Fibonacci sequence, the closer you get to the real golden ratio, which is something like this, which is about 1.618 something. And we can look at the Wikipedia article about this, which says phi, yeah, here we get the golden ratio, and that's 1.618. And you can see a formula here for the real golden ratio. The Fibonacci sequence starts to approach the golden ratio as the further you go, the closer you are to this number. So what the heck does this number have to do with our pattern that we're creating here and our angle? So the best angle to get here is 360 degrees, or a full rotation, divided by the golden ratio. So that's phi. And a formula for phi is 2 divided by the square root of 5 plus 1, which sounds very random. You can derive that with some math, but this is something like 1.618, and we can actually see that if we open a little calculator or Python console, which is the same as a calculator almost. We can do 2 over the square root of 5 plus 1, and we have to put that in parentheses. And that gives us something like... Oh, actually, I was wrong. I already inverted this. So it's the square root of 5 plus 1 divided by 2. That is our golden ratio. But if you invert it, you get almost the same thing. Okay, so now we get 1.6. I don't know if this is visible on the recording. Now we get 1.618 something. The angle we want to choose here is this golden ratio. And we want to take 360 divided by this whole thing, which is 222 degrees. And so if we copy this whole number and plug it in to our angle, that is when we get the best pattern for a flower. And it looks pretty well distributed. And you can't see any clear like streaks that we got when we kind of moved it around. So now you can see these clear lines going on, which means the distribution is not very random or not very well distributed, not evenly distributed. But if we take this number and plug that in, we get something really nice. And instead of plugging in a number, which kind of rounds it off to 3-digit after the point, we can calculate it in nodes. And I believe that the precision will be better if you do it in nodes. So instead of 360 divided by the golden ratio, we can simplify it a little bit. So let's get out of there and look at our nodes. So this is our golden ratio, and we have to take 360 divided by this, which is the same as multiplying with the inverse of this, which is simply flipping this around to square root of 5 plus 1 divided by 2. So this times 360 is our golden angle or something. And that can be simplified to simply square root of 5 plus 1, and that thing times 180, because we're dividing by 2, and times 360 is the same as multiplying by 180. So that's our golden angle. Okay, so let's recreate this in nodes. So we start with the square root of 5, we add 1, and we multiply with 180. So it's 3 nodes. Let's do that where we calculate the angle. Okay, so we get, let's duplicate this and set it to a square root of 5. And the reason I want to do that is now I don't have to round any numbers. So I can use the whole number of 5. I can subtract 1. Subtract 1. And then I can multiply that with, I multiply that by 180. And that gives us oh, we're clamping. That gives us this result, which is a little bit more precise. If we can hover over this, see that it's kind of similar. It's like 222, but we get a little bit more precision now. So I prefer to do this because if you move out a lot, you start to see some imperfections if you round it off. And now we are as precise as possible, I think. And we could have also calculated this in radians directly using pi instead of 180. But then with pi, again, you're rounding things down, or you're losing some precision. So I like to calculate it properly with whole numbers and then letting the nodes do the calculations with pi and everything, because I believe that it's slightly more precise. All right, so now we calculate the angle. There's one thing about the distribution here, that it looks like the points over here are way more tightly packed together than the points over here. And that is simply because we're moving them in a constant rate. As we increase the point count, we're moving the points out at a constant speed. And of course, the amount of points that lay on this kind of area are the same as the amount of points that lay on this area, but this one is way bigger. That's why they are spaced out a lot more. So what we're kind of doing is moving the distance in a linear way, but instead we should try to move the area in a linear way. And I don't know if that makes sense, but like the area is the distance squared. And so the area goes up like this as a function of distance. So if we want to, instead of moving the distance in a straight line, we want to move up in area in a straight line, we have to calculate the distance. So what is the distance if we know the area? The distance, and maybe this is not equal, but it's like, it's proportional. So the distance is proportional to the square root of our area, because that's like the inverse of doing the square. So in other words, we have to take this distance that we calculate and we have to take the square root of that. So let's just plug in a square root over here and see what happens. And this is going into 2 directions. Yeah, that's because... All right, let's plug it in there and plug it in there. And that changes everything by a lot, so we can increase the spacing. But now look at how beautiful this is kind of distributed, and it looks like the seeds of a sunflower or something. And this is the pattern that occurs in nature a lot. So as we animate this, we get this really cool effect of these points moving out. And yeah, we did a lot of math. Let's put this back in here. And that's pretty much what I wanted to cover. I want to add a few more bonuses. So about the animation, we just added 2 keyframes and we have this animation. If we play it back, this is what it looks like. It kind of eases in and it will also ease out based on the default. But if you want to customize that a little bit more, we can go into the animation tab and turn this into a graph editor. And here we can see what the animation curve actually looks like. So by default, you get these handles, but we can change the interpolation type by hitting T, and we can set it to linear. So this is a way more boring looking animation because the speed is all the same, but we can also choose something crazy like exponential, which looks like this. So now it starts off really slow. It's only 1 point and they're appearing really slow. And then they slowly start to speed up and it will go crazy. And then it will very abruptly stop at the end. So instead of this exponential curve, I want to also slow down exponentially. In order to do that, we select the first point and we are setting the easing, changing the easing to ease in and out instead of only in, and that gives you this kind of crazy looking curve. So now it starts very slow and it goes faster and faster, and when we're somewhere here it goes quite crazy. And there's going to be multiple points added per frame, so that's really crazy, and then it slows down slowly again. So I like, for this kind of pattern, I like this more extreme animation. So that's one thing I wanted to share. And of course, these points don't look that good. So instead of the points, we can add instances on points. And we want to add an instance of something that looks a little bit prettier. So maybe an icosphere. So we can plug that into the instance. And that gives you this, and then you can increase the subdivisions to make it more smooth. And that's pretty cool, but now the radius is not being used. So if we look at this radius of the points, we're not doing anything with it. So but we have a radius here that we can control. So let's plug in the radius there and see what happens. And now this whole noodle becomes red. So that means something is wrong. And we can see this warning message, invalid link. What does that mean? Well, the icosphere doesn't have any idea what we're doing with our index. And if you track back from this, so the way we calculate this radius is by using the index, but this icosphere has no idea what index means, because that is only something we have on the points. So instead of plugging in this radius, I'm going to keep it at 1, and we can plug it into the scale of our instance on points. And that's kind of weird to plug in a value into a vector, but what that does is when this is 0.5, the vector becomes x, y, and z all become 0.5, and that's exactly what we want. So we don't have to bother with converting this to a vector. We can just plug it in directly, and that works. So now we have something we can control here, and we can control the subdivisions, and now it looks a little bit better, and the dynamic radius still works like this. So that's pretty cool, and it's kind of fast. So let's look at the beginning. They're slowly scaling up and moving out. And if you want to tweak the way these appear, because now they're kind of overlapping, as you can see, you can always come in and go to the way we calculate this radius. Of course, you can play with the spacing, but if you like the spacing of everything, but only in the beginning you don't want this to overlap, you can play with these two numbers. So from min and from max of this map range node. And so you can start off scaling up later. So that's by increasing this one. And you can also keep scaling longer. So increasing this will make everything in the beginning smaller. So you can play a little bit with that. So you can make them scale up faster by increasing the from min, and maybe something like minus 0.5. And let's see what that looks like. So they scale up a lot faster. So let's go to the beginning where things move slower. And you can see they scale up a lot faster. They're still overlapping. If you really don't want them to overlap, you can increase this value. And you can increase it to something like this. Now they're like pushing each other out a little bit more. But yeah, you can play with that to change the look and feel of this. One last bonus tip or feature that I want to add is between the points and the instance on points, I want to add some randomness to this. So let's look at the end where we have this. It looks too perfect. So let's add some randomness by setting the position of our points with a set position node. And let's plug that in here. And in the offsets, let's make some noise happen there. Plug in the color of a noise texture, and that moves everything. Let's see what that does. It kind of moves everything in a X, Y, and Z direction. So if you don't want that, you can turn off normalize, and that will move everything more randomly around 0. So that keeps everything kind of, on average, things stay at the same location. So that is a little bit better. I want to reduce the scale because now every point is kind of moving in a random direction. And this noise is based on a vector, which is by default set to the position of the points. So if we reduce the scale, the points that are next to each other will move in a similar direction the lower you go with this. So something like 0.2 will give us a really nice, maybe even lower, gives a really nice wavy pattern. And I also want to be able to scale this. So let's add a scale, and we're converting a color to a vector, which a color is red, green, and blue, and a vector is X, Y, and Z. So that's fine. That's just 3 numbers, and that works fine. So now we can scale up and down this noise, and that's pretty cool. But one more thing I want to do is now over time, things are not moving at all. When they're moving out, it looks like it's kind of waving, but that's because they are moving in a random direction based on the location. But when the location stops changing, things stop moving. So if we want to keep moving things around a little bit using some kind of noise, we can turn this into 4D noise, which is based on a position X, Y, and Z, and a 4th dimension, which is, we can make it time. So we can plug in seconds over here that we get from the scene. And now things are kind of moving around more randomly. And we can also scale this by multiplying it. And that gives us a little bit more control over how fast this is moving. And I think 2 is kind of nice. So in the beginning and end, the position of the points are not very moving very fast, but we still have this scene time that is pushing this noise around, and that makes everything look a little bit more organic, which is an interesting effect, I think. And that will make it appear something like this, which is pretty cool. And this is our final result. And here it's starting to go crazy, and I kind of want to remove this, these annotations, because they're kind of distracting. Then we go kind of crazy, and at the edge, things are already kind of slowing down, but it's still kind of waving around because of this 4D noise. So that's pretty cool. Let's clean this up by, let's move this to the end. Then we're setting the position and then we're adding the noise. Let's separate all of this into their own little frame, and we can call that add noise. Oh, and here we have all these notes. We can just hide that for the time. Okay, that is it. That is our Fibonacci pattern. This is the way flowers put their seeds in a circle. And it's also how a pineapple, like the shell of a pineapple kind of looks. Yeah, this is pretty cool. I might have some other ideas that I can add to this that I want to share, but for now, that's it. I think this was long enough. So thanks for joining. Thanks for watching. Hope you enjoy, subscribe, and I will see you in the next one.